Hi, my name is Griffin Rice, and this is my report for Lab 1 charge tapes. The purpose of this lab is to observe the transfer of electrons between charged objects and create a computational model to estimate the amount of charge transferred based on interaction between two charged pieces of tape. Our initial conditions are the tape's length, width, mass, and we're assuming that the length of an atom is 1 times 10 to the negative 10th meters. Our system for this experiment is the hanging charge tape, and our surroundings are the second charge tape held below the hanging tape and gravity. Some observations from the experiment were that when one tape was held under another tape hanging from two elevated objects, it caused the hanging tape to float upward. Both the tapes used measured 0.2 meters in length and 0.0002 kilograms in mass, as mentioned before in the initial conditions. Both were charged by being stuck to another tape of similar length and quickly pulled off. Both were found to be positively charged since they attracted to my hand, a neutral table, and a negatively charged pen, but they repelled each other. This means that they lost electrons when they were charged, and that equates to about 8.75 times 10 to the 10th electrons lost per tape. The hanging tape was raised to a distance of 0.03 meters above its resting position when the other tape was placed below it. And the resulting forces acting on the hanging tape were the gravitational force and the electric force from the second tape. And since these forces acted entirely in the y direction and the momentum of the hanging tape did not change, the net force on the hanging tape must be zero, and therefore both forces must have equal magnitudes. From the computational model, the magnitude of the charge on each tape is estimated to be about 1.4 times 10 to the negative 8th coulombs. Given that the length of an atom is about 1 times 10 to the negative 10th meters, the model determines the number of atoms on the sticky surface of the tape to be about 4 times 10 to the 17th atoms. Therefore, the ratio of number of electrons deficient to the number of atoms on the sticky surface is 4.571 times 10 to the 6th atoms for every electron lost. We're able to calculate this by assuming that each tape lost the same number of electrons when it was charged. Here's the code used in the computational model. On the left are all the initial conditions and constants. Then we have the calculations, calculating the forces acting on the tape, the number of electrons lost on the tape to make the tape charged, and the ratio between the number of atoms and the number of electrons lost. And at the bottom we have the code creating the point charges and vectors seen in the visual display. Some of the assumptions we made that could have been possible sources of error. We treated each tape as a point charge, not accounting for the fact that the charge is spread out across the surface of the tape. We also assumed that each tape had an equal amount of charge and did not account for charge lost through handling the tapes. To answer the what if question, if the charges of protons and electrons were flipped, the tapes would instead be negatively charged. Although this still means that they will repel each other since they have like charges and attract to neutral objects, they would instead repel a negatively charged pen since they would now have like charges. To answer the why question, it is important to handle charged tapes as little as possible because charged objects tend to neutralize themselves by gaining back some of their electrons when in contact with a neutral object, such as your hand. Alright, some concluding thoughts. The phenomenon of objects becoming charged by losing and gaining electrons is more common than we often think. It can actually be fairly easy to charge some of the items we use on a regular basis. And gravitational force still plays a major role in influencing forces between charges at the atomic level, despite the fact that the particles it acts on are almost impossibly small.